All right, in this section, we're going to be talking about systems of linear equations. And so things that look like this, right? Two linear equations, and we want to find a solution. So I think this is something that you have done quite a bit and are very good at. So this should be more of a review. So we'll talk about how we solve these in just a moment. But what does it mean for something to be a solution, right, to this equation? It means that if we put those values 4, 7 for x, y into these equations, we get statements that are true, right? And we can have three situations. If we have two lines, one of three situations will happen. Either the lines will intersect in one point, and we call this an independent system. It has exactly one solution, an x value and a y value, and that happens where they intersect. Or we can have an inconsistent system, where the lines are parallel and there is no solution. They don't intersect anywhere. Or we can have a dependent system where the lines are really the same. The equations are describing the same line, right? So they're going to have an infinite number of solutions. All right, so there's three ways that we have to solve a system of linear equations: graphing, substitution, and addition or elimination. That's different ways to say the same thing. So first, this says so before we figure out how to do it ourselves, determine whether the ordered pair 5, 1 is a solution to this system of equations. So to do that, we just put in 5 for x and 1 for y, and we get a true statement for the first equation, and we get a true statement for the second equation. And yes, we can see if we graph these two lines that point is a solution, right? It's the intersection point. So the first way we can solve these, if we're not given the solution, is by graphing. So we can just carefully graph these two equations. Before we can do that, we should probably put it in y equals mx plus b form. So we just rearrange the two equations and graph them. And there we go. The solution is -3, -2, where they intersect. If we do this on Desmos, that will tell us what the intersection point is. If we do it by hand, we just have to be very careful, and it's a little bit unreliable if we do it by hand, unless the solutions are something very pleasant, like -3, -2. And once we find a solution, we can always go back and confirm that it's true, verify that it's true, right? Put those x and y values into our original equations and make sure that the statements that we get are true statements. All right, second way, which is probably the most common way to solve a system of linear equations, is by substitution, right? So we've got our two systems here. To use substitution, we choose one of the equations and one variable in one of the equations, solve for that variable, and then substitute that into the second equation. So in this equation, it would probably make the most sense to use y, right? So here's the first equation. We can bring x to the other side. Now we have y in terms of x, and we're going to substitute into the second equation. Everywhere there is a y, we're going to put x minus 5, right? So we put x minus 5 here for y, and now we just have a linear equation. We distribute, we group like terms, we solve for x, right? So we've solved for one variable, and now we go back to our original equation, or with this one, either way, to solve for y, right? So we plug 8 into this equation, we get y equals 8 minus 5, we get y equals 3. So our solution is 8, 3. And we can always verify. We put those x and y values into our original equations and make sure that the statements that we get are true. All right, the third method is addition, right? We can add these two equations together to eliminate a variable. So if we add these two equations, look, the x's will go away. We'll get 3y and 2. So let's add. The x's go away. We get 3y and 2. So 3y equals 2. We can solve that for y. And once we do that, we go back to one of the original equations and substitute 2y and 2/3 for y and solve for x, right? So x equals -7/3. So our solution is -7/3, 2/3. We can verify that by putting it into our original equations. And if we were to graph to verify that solution, sure enough, they intersect right there at -7/3, 2/3. All right, let's use the addition method again. In this case, if we just add these two equations, no variables are going to go away, right? So something that we can do before adding is multiply one of the equations by a number so that once we add it, things will go away. So what if we multiplied this second equation by -3x, right? So that it will cancel out this 3x. So here's the second equation. We multiply the second equation by -3. Sorry, not -3x. We multiply it by -3 to get this equation. -3x plus x6y equals -33. And now we add the original first equation and our new second equation together, and the x's go away. We get 11y equals -44, y equals -4. So we solve for one variable. Now we go back to either of these original equations. The second one would be easier, but they chose the first. We get 3x plus 5y equals -11, right? That's just the first equation. We substitute that y value in for y and do the work that we need to solve for x, and we get that x equals 3. And again, I'm going a little fast. Of course, you can pause this video if you want to go step by step. All right, so we know our x and y pair. We can verify that it's true by plugging it into the second equation. And if we graph it, we can confirm, sure enough, those two lines intersect at 3, -4. All right, let's solve this by addition. All right, so the first thing, we have everything at x plus y equals a number, right? Sometimes we have to rearrange the equations so that they're in this form. And we look and see that looks like we're going to have to choose a variable, either x or y, and we're going to have to multiply both equations by a number to be able to cancel out once we add the two equations together for one of the variables to cancel out. So let's multiply this top equation by -5. Okay, we're going to multiply this by -5 and this by 2. So to multiply the top equation by -5, distribute things. Here we go. That's the equation that we get. Here's the equation that we get. And they multiply the second equation by 2, right? The reason we've done this is, look, this top equation is -10x, this bottom equation is 10x. We add the two equations together, our new equations. The x's go away. We get -35y equals 140, divide by -35. We get y equals -4. Now we choose either of the equations. They chose the first one. To plug -y in, we solve for x, -2. Our solution is -2, -4. We can verify. Okay, so this is pretty much as hard as a problem can get with a system of linear equations. Sometimes you have to multiply both equations by numbers, and there's not one right way to do this, right? You could multiply by the top one by 5 and this one by -2, or we could try to eliminate the y. We could multiply this by 10 and this by 3, and then eliminate the y, solve for x, and then solve for y second. There's different ways to do it. You obviously should get the same answer any way that you do it. And then we can graph those two equations and see that they do intersect at the point that we got for our solution. Okay, what if, I guess sometimes we could have fractions, right, which are kind of a pain. It'd be nicer if we didn't have fractions. So one thing we can do is multiply the equations by numbers that get rid of the fractions. So let's look at this top equation. If we multiply everything by 6, those denominators will go away, right? And we're just left with this. If we multiply the second equation by 4, those denominators will get cleared out, and we're just left with 2x minus y equals 4. So then we have this system of equations. They multiply the first equation by -1. So sorry, they multiply the second equation by -1. So 2x plus y equals 18. This second equation they've multiplied by -1 to get this so that they can use addition and eliminate the x variables, right? So we get y equals 7. We choose either of the equations and solve for x. And they write x, instead of 5.5, they wrote it as 11 halves. Our y value is 7. We can plug those into our original equations to make sure that we've done all the math right. All right, here we've got a system of equations. How should we solve it? We could, really either way would be just as easy for this. We could just use substitution, put this in here. We could bring the 2y over here and add, or we have to multiply by -1 and add. They choose just to use substitution. They put 9 minus 2y in for x into the second equation. Do the math, and they get 9 equals 13, which seems suspicious. What happens if you get something like that? 9 equals 13. Obviously not true. What does that mean? It means that there is no solution. Okay, we have an inconsistent system of equations. The two lines are parallel. And if we put them in graphing form, y equals -1/2 x plus 9 halves, we see they have the same slope, right? So anytime two equations have the same slope, they're the same line or they are parallel and they will have no solution to that system. All right, what about this one? How should we solve this one? Looks like they're going to use addition. So they're going to multiply the top equation by -3 to get this. We add the two equations together and we get that 0 equals 0, which is true, but not very interesting. Anytime you get an obviously true statement, like 0 equals 0 or 2 equals 2, what does that mean? It means you got the same line, right? They're just two. If we put these in graphing form, we would see that they have the same slope, the same y-intercept. These are two equations describing the exact same line, so they have an infinite number of solutions. Oops. And that is the end of systems of linear equations. Hopefully this sounds familiar, and this has been a quick review, and you feel really confident with these. If you need a little more practice, the homework will be sure to give it to you.